Hello friends, this video on dual nature of radiation and matter part 7 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 6 before going ahead with part 7. Nobody told that light does not have wave nature. Okay, that is correct. Light has wave nature, but at the same time, there is some particle nature of light as well. So we will see how that particle and wave nature, they took their respective places. For now, we will see who solved this mystery of photoelectric effect. Who could explain the photoelectric effect? It was nobody else than Albert Einstein who came up with a very satisfactory explanation of photoelectric effect and brought back the particle theory of light. So Einstein again proposed particle theory of light. What did he say? He said that radiation. So here, in this entire lesson, wherever we are talking about light, since light is, something which we always talk of. So instead of light here means radiation, because light is also a form of radiation. So he told that radiation consists of discrete units called quantum of energy of radiation with energy h nu each. So he told that the radiation consists of small particles. Those particles are known as photons. And each particle has energy given by h nu, where nu is the frequency and h is Planck's constant. So Einstein worked hard in this field and he derived this. Now, do you think it was very easy for everybody to accept this? That okay, Einstein came and he told that okay, wave theory could not explain, particle theory will be able to explain. So light consists of photons and each of them has energy h nu. Nobody, accepted it as it is. So Einstein had to satisfactorily explain each and every observed experimental behavior of the photoelectric effect. So Einstein gave an equation which is popularly known as the Einstein's photoelectric equation, which was able to satisfactorily explain all the observed behavior of the photoelectric effect. So what was Einstein's photoelectric equation? Einstein told that what happened when radiation falls on the metal plate, that radiation is nothing but a number of photons, each with energy h nu, falling on the electrons. So that photon will interact with the electron. So the electron will actually absorb the photon and it will gain some energy. So if the amount of energy which the electron gains is greater than the work function of the metal, then the electron will escape out. Right? So he said that h nu is the energy which the photon has. This h nu energy is absorbed by the electron, right? So this h nu energy, when absorbed by the electron, is used for two purposes. First, it is used to overcome the work function. Now, if suppose it is greater than the work function, if this h nu is greater than work function, in that case, photoelectric effect will take place. Because if it is lesser than the work function, in that case, photoelectric effect will anyways not take place. Because the work function is more, so the metal will keep the electron with itself. But if this energy of the photon is greater than the work function, then electron emission will take place. Now, when electron gets emitted, the electron will have some velocity, so it will have some kinetic energy. So the remaining part of this h nu will be used for the kinetic energy of the electron. Now, how much kinetic energy the electron will have? What would be the kinetic energy of the electron? So there are different scenarios. The first case is if h nu is lesser than. So the first scenario is h nu is less than the work function. What will happen? No photoelectric effect. What happens if h nu is just equal to the work function? That means the energy of the photon, the electron absorbs the photon and its energy becomes exactly equal to the work function. In that case, what will happen? It will be just able to overcome the work function. So the kinetic energy of the emitted electron will be 0, because there is no more energy left with the electron, right? It is something like this is the total energy which the electron is absorbing. So this is the total energy which it has. For example, let us suppose your mom gave you 10 rupee, gave you a 10 rupee note. Now you go to a shop with those 10 rupees in your hand and you want to buy stuffs, right? Suppose if you buy a notebook worth 10 rupees and after that if you want to buy a pencil, you are not left with any more money. So when you don't have money, you cannot buy a pencil. So similar is the case here. The total energy. So here who is the mother? Her mother is the radiation. And who is the sun? The sun is the electron. So here the mother is the photon. Photon or radiation, whatever you call it. So the sun is taking the 10 rupee note, that is the energy h nu, from the mother. The mother is the photon. So now the sun has this much energy h nu. So this energy, first the sun has to spend the energy to overcome the work function, because if it is lesser than work function, anyways the electron will not be able to move out at all. It will remain in the metal. So it will first see if h nu is equal to the work function or not. If it is exactly equal to the work function, that means the total energy which the electron had absorbed, entire energy is used up in overcoming the work function. So no more energy is left to be used as kinetic energy. So the kinetic energy is 0. Now, when the h nu is greater than phi naught, in that case photoelectric emission will take place and there will be a kinetic energy also. So what will be the kinetic energy? H nu minus phi naught. So whatever is the difference, that would be the kinetic energy. So that means any electron emission which is taking place, that kinetic energy can vary from 0 to this value. So this is the maximum value of kinetic energy. Kinetic energy cannot have a value greater than this, right? This is the maximum kinetic energy that a photoelectron can have. So we can say this is K max, which is equal to h nu minus phi naught. And this equation, h nu is equal to phi naught plus maximum kinetic energy. This is known as Einstein's photoelectric equation. So I hope you understood how Einstein derived his photoelectric equation. Okay, so now we will see how Einstein was satisfactorily able to explain each and every point that was observed during the experimental study of photoelectric effect. So from this Einstein's equation, what all did we see up till now? We saw that if an electron is very tightly bounded to the metal, in that case the work function will be higher. So that means in that case most of the energy, that is most of this h nu, will be used up in overcoming this work function. Therefore very less energy will be left for it to be used as kinetic energy. Right? So this is basically the concept on which this Einstein's photoelectric equation works. So this is a very, very important equation which will explain the entire photoelectric effect. Just with the help of this one equation, you can explain everything, every observation which you saw in the photoelectric effect experiment. Let us now look at the explanation which Einstein gave to all the experimental facts that were obtained regarding photoelectric effect. The first one was photocurrent is directly proportional to the intensity of incident light. This is what we observed, right? So how did Einstein justify this? Now Einstein said that now my incident light is nothing but photons. So as we increase the intensity of incident light, we are actually increasing the number of photons, right? Now as the number of photons increases, the number of electrons with which the photons interact will also increase. As a result, the number of photoelectrons emitted increases, and number of photoelectrons is which determines the photocurrent, because photocurrent is nothing but number of photoelectrons per unit time. So therefore, as intensity increases, the photocurrent also increases. Saturation current is found to be proportional to the intensity of incident radiation. That is also related. I mean, number 1 and number 2 are related to each other, because saturation current is also nothing but photocurrent. It is the maximum value of photocurrent. So obviously, as you increase the intensity, saturation current also increases, because increasing intensity means increasing the number of photons. Therefore, the number of electrons will also increase. Therefore, the photocurrent increases. And after a certain level, there are no more electrons left to absorb the photons. And as a result, the current becomes constant. And that is what is known as saturation current. There exists a threshold frequency for every metal below which no photoelectric effect takes place. Now let us look at the Einstein's equation. What was Einstein's equation? It was h nu is equal to phi naught plus k max, right? This is Einstein's equation. So it says that photoelectric effect, under what condition photoelectric effect will take place? Now for photoelectric effect to take place, what is the condition we just discussed in the previous slide? It can take place only when h nu is greater than the work function. So that means now what happens if I say that no, if I say that h nu is less than phi, what will happen in that case? If h nu is less than phi, in that case, what will happen to this k max? This is h nu minus phi naught. Since this is lesser than this, so this k max will become negative, which is not possible, because can kinetic energy be negative? Kinetic energy can never be negative. That means your h nu can never be less than phi naught. What does this imply? This implies that h nu can either be equal to phi naught or it can be greater than phi naught. So when I am talking about the threshold frequency, I am talking about the minimum value. So what is that minimum value? That is h nu is equal to phi naught. So this value of nu, this minimum value of nu is known as threshold frequency, and it is generally denoted by nu naught. So we define nu naught as the threshold frequency, and we say that work function is equal to h nu naught. So this is how we define a threshold frequency. So Einstein's photoelectric equation can also be written as h nu is equal to h nu naught plus k max, where nu is the frequency of the incident light and nu naught is the threshold frequency at which and beyond which photoelectric effect takes place. Correct? Okay, so now you will see that Einstein will be able to explain all the facts using his equation. Next one, it says that stopping potential is independent of intensity of incident radiation. If you see here, stopping potential, what is stopping potential? Stopping potential is E V naught is equal to K max. Right? So stopping potential is related to maximum kinetic energy. And if you look at Einstein's equation, kinetic energy depends on frequency. You can see the term nu in this equation. But is there any term for intensity? No. So stopping potential is independent of intensity. Stopping potential and maximum kinetic energy of photoelectrons increases linearly with frequency. That is getting very clear from the equation. If you look at the equation itself says that this kinetic energy is directly proportional to nu, that is frequency, and kinetic energy is again directly proportional to stopping potential. So the stopping potential is also directly proportional to nu. If you look at this equation, it comes out something like this. K max is equal to h nu minus phi naught. You can also write it as E V naught is equal to h nu minus phi naught, or you can write it as V naught is equal to h by E into nu minus phi naught. So if you look at these two equations, they tell you that the relationship between kinetic energy and frequency, both these equations are of the form y is equal to mx plus c. So if you plot your potential along y-axis, and if you plot what is x, x is frequency. So if you plot your frequency along x-axis, you will get a straight line, right? You will get a straight line. And what is this phi naught? It is nothing but the intercept. You all have studied all these things in your mathematics, right? That how do you plot a graph y is equal to mx plus c, and what does this signify, right? So what will happen when nu is equal to 0? If this frequency is equal to 0, when frequency equals to 0, what would be the value of V naught, stopping potential? It would be minus phi naught. That means V naught would be somewhere in the negative axis. So the plot will be somewhat like this, and this value is nothing but the threshold frequency. So this is how the plot will be. So that means this equation itself, from Einstein's equation itself, you can plot the graph between stopping potential and frequency. Similarly, in this case, here Kmax will be taken along y-axis. So you see that you can arrive at this relationship that maximum kinetic energy and stopping potential, they increase linearly with frequency, right? So now you see Einstein was able to cover all the points which were experimentally observed regarding photoelectric effect, which the wave theory of light failed to do. So that is how Einstein's photoelectric equation became more convincing and more popular, and as a result, people were forced to accept that particle nature of light also exists. The last but not the least, photoelectric effect is an instantaneous process. So according to Einstein's explanation, he said that when does this emission take place? When does photoelectric emission take place? Whenever a photon hits the electron. So obviously it is an instantaneous process. The moment the photon hits the electron is emitted, because the entire energy of the photon is immediately absorbed by the electron. So there is no time lag between emission of electron and interaction of photon with electron. Whereas, as I explained you earlier also, in wave theory, it was like the radiation is coming up and all the electrons are absorbing energy from that radiation. So gradually they will have enough energy to overcome the work function. So there was a time lag involved. But in this case, photoelectric effect was an instantaneous process. So finally, Einstein was able to satisfactorily explain all the concepts. So Einstein's satisfactory explanation for the photoelectric effect confirmed the particle nature of light. So now nobody could deny that light is of particle nature, because earlier what happened was, long back when Newton gave the particle theory of light, he explained certain things which particle theory of light could explain. But later, when so many scientists came up and they studied interference, diffraction and all, and it was seen that particle nature of light was not able to explain those phenomena. However, wave nature of light was able to explain all those what Newton had explained, that is reflection, refraction and all those stuff. So everybody told that means particle nature of light is an incorrect concept and wave nature of light is the correct concept. But now, after this phenomenon of photoelectric effect, it was seen that there are certain things which wave nature cannot explain. So particle nature had to play a role. So what was the final conclusion? The conclusion regarding particle nature of light was, light consists of discrete particles called photons. So whenever light falls on any object, it is basically the photon which will interact with the electron present in that object. So let us quickly talk about the photon picture of radiation, some of the properties of photons which we have already discussed in the course of discussing Einstein's photoelectric effect. But let us have a quick review. Radiation behaves as if it is made up of particles when it interacts with matter. So now, there are certain clauses. Now people knew that radiation can behave as a wave. Radiation can also behave as a particle. So, but they behave as a wave and they behave as particle under different situations. When a radiation interacts with a matter, that means when light falls on an object, when light hits a ball, so that means it is radiation interacting with matter. So when radiation interacts with matter, radiation behaves like particle nature. Now energy of each photon is E is equal to h nu, where h is the Planck's constant. Momentum of each photon is nothing but E upon c, right? That is how we calculate momentum, which is h nu by c. All photons of a radiation of same frequency have same energy and momentum. So what is the energy and what is the momentum, that I have already mentioned. So if a radiation has same frequency, then all the photons will have the same energy and the same momentum. Energy and momentum of photon is independent of intensity of incident light. Okay, please remember that intensity governs only one thing, and that is photocurrent. Photons are electrically neutral, neither positively charged nor negatively charged. In photon particle collision, total energy is conserved, total momentum is conserved, number of photons may or may not be conserved. That means when a photon hits an electron or hits any other particle, what happens? Total energy will remain conserved, because energy conservation is true everywhere. Similarly, total momentum will also be conserved. But when we talk about the number of photons before collision might not be same as the number of photons after collision. That's because during the process of collision, many times it happens that the particle absorbs photons, right? So sometimes it might happen that the number of photons before collision does not tally with the number of photons after collision. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.